Our last situation is where we're going to determine the pH and percent ionization of a 0.1 molar solution of acetic acid, which is CH3COOH, and it has a Ka value of 1.8 times 10 to the negative 5. And whenever you're given a Ka value, that should be a hint that this is a weak acid and not a strong acid, and so we have to approach it differently. And so when we're looking at this one, the concentration of CH3COOH does not equal the concentration of H3O plus. And that is because CH3COOH doesn't dissociate completely. It only ionizes a small percentage. And so we have to write an equilibrium equation for that. So we start off with our acid, which is going to be aqueous, because all acids are aqueous as far as you guys know. And then we're going to add water. So that's going to act as the base in this situation, and this is an equilibrium reaction. And so you end up with the conjugate base being the acetate anion, also aqueous, and the hydronium ion. And so from this, we're going to be able to calculate the hydronium ion concentration, because this is going to be a weak acid solution. But because it's equilibrium, we can use an ice table. So I know that the concentration of this acetic acid is 0.1 molar initially, so that's my initial. My change and my equilibrium will do next. So you won't need to calculate anything for water, because water is a pure liquid, and pure liquids are not part of our Ka expression, and so nothing needs to be calculated there. These will be zeros, because we're going to know that initially there's none of the acetate ion present and none of the hydronium ion present, and we're going to calculate how much there is at equilibrium. So this is great because acid and base reactions, acid and base equilibriums are usually 1-to-1 molar relationships, particularly when we talk about acids. All right, so we end up with this as our ice table, but our Ka value is 1.8 times 10 to the negative 5, and that's a very small number. And so because that's a small number, we should be tipped off to the fact that we can use a small x approximation. So to determine if I can use the small x approximation, I'm going to do my initial concentration, which is 0.1, divided by 1.8 times 10 to the negative 5, and I get a number that is way bigger than 500, so I'm going to use small x. And so that's why I'm going to neglect this x on the bottom here. So my Ka expression, Ka equals H3O plus times acetate, which is CH3COO minus, all over the acetic acid concentration. Looks like that. Okay, we should always include that in our calculations. So from there, I can just fill in what I know. So I know Ka is equal to 1.8 times 10 to the negative 5. This is going to be x squared on the top, because both CH3COO minus is x, and H3O plus is also an x. So if I multiply those together, that's x squared, and we'll put it over 0.1 on the bottom. And so remember, it's 0.1 on the bottom because I'm using the small x approximation. And so if I solve for x, I get a value that is 0.00134. I'm pretty sure, just let me double check. Yep. Okay, and so that's going to be equal to my H3O plus concentration, because remember, X is what the hydronium ion concentration is. And so from there, I'm able to calculate pH. So I'm just going to go up here to do that, so I still have some room. So remember, pH is the negative log of the H3O plus concentration, and so my pH in this case will be negative log of 0.00134, which is equal to pH equals 2.87. So I have calculated a pH value, which is the first part of the problem here. It says calculate the pH. And now I have to find the percent ionization. And so percent ionization is just a measure of how much hydronium ion forms compared to how much of the original acid concentration there was. So in order to do that, I just have to take my hydronium ion concentration, which is equal to 0.00134. Sorry, I'm going to have to multiply this by 100%. I forgot to put that in there. And I'm going to divide it by the initial concentration. So what I started with of the CH3COOH, I multiply by 100%. Sorry, I'm running out of paper here. And I end up with a percent ionization that is equal to 1.34%. So you can see that this is a very small amount. So in this particular concentration of acetic acid, only 1.34% of it is converted to hydronium ion, and the rest stays as CH3COOH because the Ka value is very small, so the equilibrium lies way to the left. I hope that was helpful. I'm going to give you some practice problems via Mr. Gardner, and he will tell you which ones you have to do. Thanks.